Hello there, this is Colin B, and I'm going to see if I can help you understand how to approach this type of problem. So here we have an example problem where we're oxidizing iron metal to iron 2, which gives us a concentration of about 0.007 mole. We have a concentration of gold 3 plus is 0.5 mole, 0.05. So that's being reduced. And this gives us this overall equation. So in order to figure out, and we're trying to find the equilibrium constant at, let's say, 40 degrees Celsius. And this will have to be in Kelvin. So adding 273 to that, and you will get 313 Kelvin. So that's the temperature we're looking for. That's your first step. If you see a temperature and it's not in Kelvin, you got to know how to convert it to Kelvin, which you just add 273 to it. The second thing we need to do is we need to know what we're given. So we're given these E cell values. So iron, the reduction of iron 2 to iron metal is negative 0.45 volts, as opposed to the reduction of gold 3 plus to gold, which is 1.5 volts. So what we have to do now is we have to decide, okay, what's my standard E cell? And it can be written out as cathode minus anode, oxidation plus reduction. It's the same story. So this is being oxidized, this is being reduced. So that's 1.5 volts minus negative 0.45 volts. So we get an E cell of 1.95 volts. So this is favorable, this is spontaneous, because it's positive E cell. Okay, so that's what we're given. We're also, from the balanced equation, we can tell, okay, there are 6 electrons flowing. The way we check this is like, how do I get these two equal? I multiply this by 2, I multiply that by 3. That's that. Now, here's what we need to do. We need to write out all that we're given. Joule per mole. That times the temperature, so 313, divided by 6 mole electrons, times the Faraday's constant. Now, the Faraday's constant can be written out multiple ways, but for the most part, it's easier to write it out like that. Coulomb per mole E. Make sure your units cancel out. And they do this right there, right there, right there, right there. So, and volts is equal to joule per coulomb, so we are good. But, and whatever you get here, you're gonna have to divide 1.95 by that value. So we do that. So that's going to be equal to that. So we currently have joules per coulomb, ln of K. So divide both sides by that, by this value. Now, and when you do that, you should get a value somewhere in the neighborhood of like ln of K is equal to 433.869. Now, in order to get rid of this ln, you need to know how to do that. So we take the E of both sides. K is going to be a massive number. In fact, my calculator doesn't give me a value. So that's how we do this. Granted, if you're doing that, you need to decide, okay, this is how you would do it at equilibrium. If you're dealing with, let's just say at non-standard conditions, you would do E cell is equal to standard E cell plus RT ln of Q. That should be that. All right, I'm a little bit over time, so hopefully this provides you a little bit of guidance about how to solve this. Have a good day.